which there are some very good free ones available online. And this one actually, as you can see, is from Stellarium, which is the one I use when I teach the lab version or the lab that accompanies this class. It's very popular with educators. And like I said, it's free. All right, so the plan for this chapter is to talk about the celestial sphere. What is it? Why do we use it? And how do we work with it? Okay. Then we're going to talk about movement on the sphere. This is going to require a little bit of sort of what I call 3D visualization, being able to think about, like you looking up, but then standing on a sphere. What does that mean? Sometimes it takes a little bit of practice to be able to really kind of work with that and be comfortable with that kind of visualization. And it comes more naturally to some people than others, but with practice, I know you can all do it. Then we'll wrap up with solar system models. How do we think about the motions of the planets and the apparent motion of the sun through the celestial sphere? How does that all relate to our models? What are the historical models that have been rejected and replaced with more modern ones? All right, so the celestial sphere. So the celestial sphere is defined as an imaginary sphere that surrounds Earth. The stars live on the surface of the celestial sphere. So every star has a fixed point on the celestial sphere. And that kind of, relates to the why the stars don't appear to move relative to each other. And that's because they're so far away that the movement of stars relative to each other takes hundreds of years, so we don't notice it within one person's lifetime. So the stars are effectively fixed in place. If you do look at them historically, you go back 2000 years, yeah, they've moved a little bit, not too much, but they have moved. And so over long periods of time you would have a new celestial sphere. Okay, but they're just fixed dots for our purposes. And this whole thing of imagining a celestial sphere does have some sort of like historical tie-ins, because people did kind of imagine that the stars maybe really were on some sort of divine sphere at some point. That's kind of how they look, of course. And so that's kind of why we still use that terminology, but we're using it now just for the purpose of a tool, right? Just a thought process that we can help visualize things and define their coordinates, which we'll be talking about quite a bit. Coordinates. And speaking of a couple of special coordinates and kind of how the celestial sphere relates to Earth, also a sphere, of course, are the poles of the celestial sphere. So it's got a north and south pole, just like Earth. And those poles are exactly lined up with Earth's poles, because that's the whole idea of the celestial sphere, to make it easier to work with, is it just overlays Earth. So if you go straight down from our South Pole, you're going to hit the South Celestial Pole. If you go straight up from the North Pole, you'll hit the North Celestial Pole. And there'll be particular stars or nebula or galaxies located at those points, right? Or at any particular point, if you drew a straight line up from Earth. Of course, that line has no defined length, because the celestial sphere does not have a defined radius, because that would mean it's an actual physical sphere. It's not. It's just an imaginary one, right? But it does still have angles and points along it. Another direct kind of connection between Earth and the celestial sphere is the celestial equator, which exactly lines up with Earth's equator. So if someone stands at Earth's equator and looks straight up, they would be looking at a point along the celestial equator. So at night, they'd see some star located there. Or, that it's not just stars that we define on the celestial sphere, although that's what we're talking about now. The sun also tracks through the celestial sphere. And during the day, it's the only thing you can see because it's so bright, right? Unless it's an eclipse. And so then you could talk about the location of the sun on the celestial sphere, which could be over the celestial equator. Now, here's another thing. And I kind of pause because this term, the zenith, is not a term that relates to the celestial sphere. Rather, it's a term that relates to your local sky, which we will see on the next slide. But that you need to be able to translate or to go back and forth between the notion of the local sky and the notion of the celestial sphere. And the zenith can help you do that. The zenith is simply a point that is directly overhead. So if you're standing at some point on Earth and you look straight up, you're looking at your zenith point. And you can see, right, that here, this is some location in the Western United States, right, or at least Western North America. And for someone located there, their zenith, which is this, there's the point directly above their head, if the observer is a person, then if they would draw a line until it hits the celestial sphere, then it's going to correspond to a location on the celestial sphere, right? But any other person on Earth, their zenith would be a different location on the celestial sphere. So it's not like that zenith is a unique point on the celestial sphere, quite the opposite. Okay? So I told you that you'd see the local sky. Here it is. So the local sky is a hemisphere, half a circle. The celestial sphere is a full sphere, right? So we've got, and I think I said half a circle, should have said half a sphere. But we've got our two kind of ways of visualizing the whole sky, right? That could be seen if you mapped it out, and the sky that you can see at any individual location. Because you can never see the whole celestial sphere, right? Half of it is always obscured by Earth. So any location on Earth, you can only at best see half the celestial sphere. And that point is driven home by this figure here, where we see the local sky as a half sphere, because you're obstructed by the ground. And in the very best case, if you're on totally flat ground with no hills or buildings or trees or anything to cut off your horizon, you would have a view that goes from the horizon to the zenith and covers 90 degrees. And then from the zenith to the opposite horizon, another 90 degrees, for a total of 180 degrees of arc as your view. Okay? And we will be talking about about degrees, portions of a circle, 360 degrees in a circle, but we won't be doing any calculations with them. As I said before, no trig, no actually using those degrees for calculations, rather just having them as values. Okay? We might make a subtraction between one and the other, but that would be the limit. Okay? So I'm going to, let me define latitude and longitude, then I want to show you a simulator real fast. Time, yep, we're good. All right, so we're going to talk about coordinates on the celestial sphere, but to do that, let's make sure that we're good on Earth coordinates because they're good comparisons. My hope is that you're more familiar with Earth coordinates, latitude and longitude, so you can kind of leverage that knowledge to make sense of the coordinates that we talk about on the celestial sphere. If you're not, that's okay, but it does help. So latitude is the way that we measure as an angle the location relative to the equator. Okay, so it's an angular measurement that sweeps away from the equator. And so that angle will grow if we go towards northern latitudes, starting with 0 being defined as the equator, and it maxes out at 90 degrees, positive 90 degrees for the North Pole. So that's the largest possible latitude that you can have on Earth is positive 90. If you go south of the equator, the latitudes are defined as negative with a minimum value of negative 90 degrees. You can't go any further, because if you kept going, you would just start going into smaller, in magnitude, but closer to 0 negative values, because all the latitudes, they completely circle the Earth. And so in other words, it doesn't matter what direction you come down from the equator. And that's why latitudes only vary between 0 and 90, as opposed to between 0 and 180. Because that you'd be double counting if they went from 0 to 180. In contrast, longitude is measured around the Earth. It also has a negative and positive depending on whether you go east or west. All right. With east being actually the positive and west being the negative direction. And the 0 for the longitude isn't the equator, which is a natural, physical point between our two poles, our rotational poles, but instead is a arbitrary line that was chosen for historical reasons, um, and goes through a particular city in England, and it's because of its association with the Royal Society the and in England, and they're basically the scientists that were working, and because of the English colonial power during like the age of imperialism. So that's kind of how it happened. It was chosen as the 0 point, basically either agreed upon or forced upon the rest of the world. And we've stuck with it since because it would be very difficult to change it at this point. So now we have agreed upon 0 point. You can see runs down through this, kind of cartoonish map. We can see, right, runs down through part of England, then through some of Europe, big chunk of Africa. That's the prime meridian, the chosen 0 point for longitude measurements. Okay. So whereas latitude is all about north and south, longitude is all about east and west. Okay. Like I said, positive is in the east direction. You can see that, right? If you start at 0 degrees, the prime meridian, and you move eastward, you hit positive 30, positive 60, positive 90, 120, 150, 180. Also notice that it goes all the way to 180, unlike latitude, which maxes out at 90, right? With longitude, you can go all the way to 180 because that way we can sweep out the entire Earth. All right. And when we go the other direction, we can go all the way to negative 79.9 because 180 is a unique value. So there is no negative 180. And so in other words, the negative values approach negative 180, but don't hit it. The positive values actually exactly hit the 180. Okay. Any questions on latitude and longitude? So let me show you that simulator that I want to share with you all. So this is the Rotating Sky Explorer, an online simulator created by the Astronomy Education Program at the University of Nebraska-Lincoln. They actually have a really impressive website that gets used a lot by a lot of educators. And the reason I'm showing it to you is because it shows both the types of hemisphere and sphere we've been talking about. The celestial sphere shown on the left and the local sky shown on the right. You might think, hey, that's not a hemisphere, that's a full sphere. And that's because it is showing the part underneath the ground that you can't see. But of course, for practical purposes, we focus on the part you can actually see, which is above. I can grab it and move it around because it is a simulator. And so we can see different points, okay? So right now, I want to point out what's being labeled, okay? So we have the celestial equator being denoted by this yellow line, all right? We have the underside of the horizon diagram showing, which was talking about, so I'm actually going to turn it off so we don't see it. And we also have the 0 hour circle, more on that in just a minute, okay? That is just to kind of show you what's gonna come. Although I will say it again. It's going to be the equivalent of the prime meridian for the celestial sphere. But if that seems confusing, don't worry about it. We'll come back to it in just a moment. All right. We can change our location on Earth. All right. So let's go ahead and I think can I turn on a zenith and we show labels. Yeah. So looking at the local sky. So there's a little stick figure. There's zenith. is that point directly above their head. See? And then the horizon would just, it's not labeled, but it would just be the edge of that green circle, right? The flat ground that they're standing on. The NCP is the North Celestial Pole. SCP is South Celestial Pole, which we talked about. Okay? Notice that the celestial equator shows up in the local sky. See how it kind of arcs across like this? And that's because this person is in the northern hemisphere. So, of course, the celestial equator is not directly overhead because of where they're located. If I was to move our little stick figure down to an equatorial location in South America, and I'm just sort of eyeballing it, so it won't be exact. But now I've moved them down. You can see on this animation where they're located, or on the smaller map, the flat map, you can see where they're located somewhere in maybe very eastern edge of Brazil. And directly overhead now is the celestial equator. Since they're located on Earth's equator, the celestial equator passes through their local zenith, just to show what that means. Okay. And we're going to come back to this in a moment, but hopefully that drives home any ideas that could have potentially been confusing. Back to the slides. Okay. All right. So now I had hinted at that we were going to see the equivalents of latitude and longitude for the celestial sphere. Here they are. The equivalent of latitude for the celestial sphere is declination. Why did they give it a different name? They just did. Okay. And, I guess they could have called it celestial latitude, but they don't. They call it declination. And it's measured, no surprise, relative to the celestial equator. It works exactly the same. So positive as you go north, negative as you go south. Okay. So it's this purple line right here. See, it's measured relative to the celestial equator. So this star would have some positive declination, maybe like 60 degrees. Okay. The other coordinate on the celestial sphere is called right ascension. And by the way, declination is measured as angles, as I, obviously implied by saying that it's 60 degrees, but just to, point out, as it says in parentheses here. So is right ascension sometimes. Okay. So take note of that. The right ascension, kind of a strange name, but it's the equivalent of longitude. It's measured relative to something equivalent to the prime meridian. So some defined line that actually connects from one pole to the other, because that's how the prime meridian works. It's a half arc that arcs from one pole, the North Pole to the South Pole, for example. All right. And when you go in the direction coming from right ascension, it's always positive. So that is a key difference between longitude and right ascension. Is longitude was chosen to be split into that whole idea of either going towards the east or towards the west, and having positive in the eastward direction, negative in the west, and then 180 just about in both directions. But right ascension, the name kind of says it. Well, it's you only move to the right. So you move from the equivalent of the prime meridian, and you move all the way up to a maximum of 360. So if you're expressing right ascension in degrees, it varies between 0 and 360. Okay? So I got a question for you. The star Polaris is very close to the North Celestial Pole. Its declination is approximately what? Either raise your hand or just jump in with an answer. Or throw
Is
it in the
it
chat.
positive 90?
Yeah, it sure is. Positive 90. Yep. Alexander, you had it as well. Ace, nice. And who was it that gave me the answer over the microphone?
Alina.
Thank you, Alina. Yep, positive 90. That's the famous North Star, Polaris. Yeah, does anyone know a nickname for Polaris besides North Star? Anybody? Fine. I was just curious. It's called the Dog Star. You ever heard that? Maybe. All right. Nope. All right. Yeah. Yeah. I guess it's not maybe widely known, but I feel like I probably read it in a book or something, like a fictional book, Polaris, named after a dog in Greek mythology, probably, but I'm no expert on that. All right. So North Star. We'll be taking our break in just a minute, but I want to get to a good stopping point. So continuing with declination, right? So if you are in the northern hemisphere, you can always see a star if its declination is between positive 90 and positive 90 minus your latitude. So those are stars that you will always see in the sky. And as you can see in the title here of the page, right, that's called the circumpolar region. So if you were at, a latitude of 20 degrees above the equator, which is south of, where we are. So, that'd be like fairly south, kind of like, subtropical. And if you were at that latitude, you would be able to see any star that has a coordinate, particularly a declination coordinate on the celestial sphere between positive 90, such as Polaris, and positive 90 minus 20, which of course is 70. So that would be your circumpolar region for that particular latitude, regardless of your longitude, because longitude doesn't matter for what stars you're capable of seeing. The best way to think about that is you just got to wait to a different time of the year if you want to see different stars. So when we talk about the visibility of stars, they're going to vary throughout the year, which maybe from stargazing, and that's going to, certain longitudes are going to see certain stars different times of the year. But overall, everyone at a latitude is capable over the duration of a year of seeing the same stars. To add to that concept and bring it back to circumpolar, everyone at that latitude will always see the circumpolar stars because those are the ones that never rise or set. So they don't change throughout the year. They're always going to be visible. And over the duration of a single night, if you were to track them, you would see them move in a circle. So even over a given night, they don't rise or set. And if you've ever seen those time-lapse photos that show stars as streaks, well, these would end up as circular streaks because of their particular orientation in your local sky. And I'm going to show that in the simulator, and then we'll take our break. And good. Dun, dun, dun. There we go. Okay, back to the simulator. We were currently located at the equator, but let's go up to a latitude of 20 degrees, like I was talking about. All right, and make it north. There we go. All right, looks good. And then we're kind of in the Caribbean somewhere. Kind of, yeah, there's probably an island there if you look where the dot's located. All right. And now I'm going to turn on the option that's actually going to show the circumpolar stars. So this is the circumpolar region for someone at this latitude. They can see stars that never rise or set between 90 degrees, because remember that's 90 degrees on the celestial sphere, and 70 degrees north on the celestial sphere. So it's kind of just a small region of stars that would never rise or set. Okay. And if we look at it on the celestial sphere, we can see it's just a small top. If we were to increase their latitude and consider an observer that is, like say in the Arctic, so above, um, the Arctic starts at 67 degrees. So let's put them at like 75 degrees north. They have a much larger circumpolar region. So now most of the stars in the sky will not rise or set. You see it on the celestial sphere because now that circumpolar region includes stars from the pole all the way down to 90 minus 75, which is 15 degrees. So, how large would the circumpolar region be for an observer at the North Pole? Anybody know? Want to venture a guess? If this is, and just describe it however you think best, makes sense to you. Like here you would, if you wanted to say how large is the circumpolar region for an observer at 75 degrees north, as I just said a moment ago, it's most the sky, right? It's a good amount of the sky. We're looking at a little observer here, right? You can see it, good portion of the sky is the circumpolar region. But what about someone that's all the way at the pole? Yes, Trinity, you got it. Nicely done. There you go. The whole sky. No stars rise or set. Every single star in the sky will make a circular route. And they actually will all be parallel to the horizon. So all the stars, some of them obviously would just like kind of skirt along the horizon and realistically would have to get obscured by something. But if the ground was perfectly flat, you would see, some of them going right, kind of kissing the horizon the whole time. And then they're just, as you look up, they would all just take paths that are exactly parallel to the horizon, circling around. Okay. Obviously, the motion of stars in the sky over the duration of a night is slow, so you don't notice it with the naked eye. But over a couple of hours, it's quite noticeable with a long exposure. So this, because it's the apparent motion and it relates to Earth's rotation. And so, if you were up at the North Pole during the time where the sun never rises during the Arctic winter, and you'd be able to see the stars 24 hours a day, and if you were to track them, they would take exactly 24 hours to make a full circuit, a full circle in this entire circumpolar region. All right. Yeah, so YouTube videos, the ones absolutely, the ones that I have, the lectures, the instructors that are tied in, my instructor, my own videos, but I think that you'd find it really similar to what I'm saying here, although obviously sometimes just referring back to it's helpful. There are tons of other ones if you just do a quick Google search for any of the key terms that we're talking about here, like like how do I understand the celestial sphere? Understanding the celestial sphere. You can find lots of options, but I do have linked videos under the pages that have the chapter name and say videos and slides. All right, so let's take a 5 minute break. Let's make it 6 minutes, and we'll come back together at 11:25. So I'm going to mute everything on my end, and then I'll see you all in a few minutes. Okay. So I'm going to move back to the slides. All right. Okay. Close that. Okay. So we had just been speaking about the circumpolar region, and we had basically wrapped that up. So let's take a look at the opposite, the never rise region. These are stars that we will never see at a particular latitude. That's why people talk about southern hemisphere constellations, ones that people who live in the northern hemisphere at northern latitudes never see because they're always obscured by the planet. Okay. And their latitude, or rather their declination, is defined by your latitude in the same way that the circumpolar stars have a declination defined by your latitude. The formula for finding out what the region looks like, how it extends, would be -90 plus your latitude. But that'd be the lower limit, and the upper limit will just be -90. Okay. And that's going to apply for really specifically someone that's in the northern hemisphere. And I think that, I mean, it does say that. And that's, yeah, that's so both of these inequalities only apply to the northern hemisphere. If you want to use them for the southern hemisphere, you have to change all the pluses to minuses, so all the positive values to negative ones, and vice versa. Okay. All right. So I think that it's similar enough to the circumpolar concept that I won't show it in the simulation for now because I want to get on to some other concepts. But if need be, we can circle back to it later. Okay, so there we have this idea of star rising and setting is everything in between. So stars that rise and set over the duration of a night are the ones that are between those two regions. All right. So we can see here that we have the never, or rather, we have the circumpolar region shown in red. We have the never rise region shown in blue. And that band in between are the stars that would rise and set. So at a particular time of the night on a particular day of the year, they will rise and then they will set. Okay. And those rise and set times will change throughout the year, but these stars will always rise and set. So the star Antares has a declination of -26.8 degrees. Oslo, Norway is at a latitude of 60 degrees north. Can Antares be seen in Oslo? Who has an answer? Let me check the chat as well. Okay. Okay, so a bunch of people say no, it can't be seen. All right. So mostly we've had people vote for no, which would be one. But let's take a look at the formula. Okay. So we have, I'll just do it right here. All right. So let me change the view. Okay. So, okay, we're opening the wrong thing. All right. So there we go. So the correct answer is actually two, which, to be fair, at least I saw one person, maybe two, because I think as I was closing the chat, I saw one other person venture a option of two. And I can see why. You thought it would, wouldn't be visible because, hey, I mean, it's a southern star, right? Negative 26.8. It's, below the celestial equator, and Oslo's pretty far north. But presumably that was chosen on purpose by the authors because it's just barely visible. So it would be a rising and setting star. And just to show that real fast, if you think of the inequality here, we have stars that are between 90 degrees, right? That's going to be that, so you can see those ones just fine. And I'm doing the inequality the opposite way, I think, putting the 90 on the left, but I have the correct direction there. And so then we have our star, right? So Antares, right? So obviously Antares is between positive 90. But then if we take the difference, right? So if we look at, what, how small can it be? Well, we can see stars to a point of the latitude minus 90 degrees. Okay. So it would be 60 degrees, which is the latitude, positive 60 because it's north, and then minus 90 degrees. Well, 60 minus 90 is negative 30. So then this inequality becomes, I'll just cross it out and write the result, negative 30 degrees. So Antares is within that range. In Oslo, someone could see a star as that has a declination as far south as negative 30 degrees. All right. So stars at the zenith, all right. So stars with the same declination as your latitude will pass through your zenith every day. All right. So that means that if you can locate a star at your zenith and you know what that star is, you can locate your latitude. And this was a key thing with historical navigation. And from, ancient times on, it was fairly easy for accurate measurements to be made to locate, even in the open sea where you can't see land, to locate someone's latitude. Finding longitude was much more difficult, and basically actually came down to having a reliable clock that continued to measure time even on a rocking boat. And that actually was a major breakthrough that came in the 1700s, and really took off and became widely available in the 1800s. So that was the key of actually being able to know your longitude, because that way you could know the exact time that the sun rises and sets and use that to calculate your longitude. But you had to have a clock that kept running the whole time, because you couldn't, if it stopped, then you wouldn't know the exact time. Okay. But just looking up at the night sky, as long as it wasn't cloudy, you'd be able to locate your own latitude by finding a known star at your zenith. All right. So you can do lots of exploration with Stellarium, but also with, like the simulator that I was using, although that one doesn't show the sky, but it still is a great visualization tool. All right. We're skipping this. All right. So Polaris and the zenith. All right, looking at different points. Okay, so these links take us to Stellarium. So if we wanted to look at what the night sky looks like at these different points, I'll go ahead and do one for us. Let's see. So we got all these different locations. All right. So let's try one that's pretty far south initially. So I'll turn that off. Come on. Yeah. What to do? No, just don't want the pen on there. All right. Yep. Good. I'll switch so you can see it, because right now I know you're still seeing the slides. All right. Yeah. Oh, cool. Yep. And some people took note of how the answer works out. Nice. All right. So this is I followed the link to see Polaris. So this is although here let me reload it because I accidentally clicked away. All right. So there is Polaris as seen from Mexico City. All right. So a northern latitude location, but a relatively small latitude, right? Much closer to the equator than say, Canada. All right. Now I'm just going to click on another one and it'll reload and I'll show you what Polaris would look like from a different location. So I'm going to jump ahead to Lincoln, um, Nebraska. So, obviously, further north. Ah, notice, right? Polaris is now further above the horizon, right? Polaris was pretty close to the horizon. What if you do Winnipeg? Okay, further still, right? And it's kind of a strange effect that it's hard to fully appreciate how much higher we are above the horizon because as we start looking up and the sky dominates, our view, it gives us a different perspective of about like kind of what the horizon looks like because straight overhead is going to be probably kind of right around where my mouse cursor is. Okay, but let's go ahead and do Resolute Bay, Canada. So, one of these incredibly northern outposts. Okay. All right. And we can see, right, it's even closer to the horizon. I know it's during the day, so it's not visible. Let me change the time real fast. So let's go ahead and I can find the time settings more easily. It's saying, oh, it's like I'm used to using not the web based one. And there's just like a real quick way to advance between time. Oh, that's too bad. I can't find it anywhere. Is it obscured at the bottom? Yep. There we go. All right, so let's move forward in time. No, let me reload that one more time. Sorry. Okay, so back to Canada and constellations, atmosphere. Still not quite the same settings, but there's familiar enough with them, but I'm still not seeing the time one. Oh, I bet it's just right here. There we go. Yep. So I'm just gonna drag us to nighttime. Oh, that's why. We're we're approaching the longest day of the year. The sun never sets. Oh, well, that's not gonna work. We won't really be able to see it. I could actually turn off the atmosphere. So I can go here and just turn off the atmosphere, force it to become night. So you can kind of see stars. So like the sun is still up, but and by the way, if there was no atmosphere, this is what the sky would look like. We would see the stars all the time, even though the sun is bright. The only reason we don't see stars during the day is because of the atmosphere and the scattering of the light. So on like Mercury, right? Really close to the sun. The sun obviously is huge in the sky, but it doesn't obscure the stars. You know, you just have to not look directly at it, and you'd be able to see the stars because there's no atmosphere. All right, there is Polaris, and finally to drive the point home, we got the North Pole, where Stellaris is directly overhead because of the time of the year. It's perpetual light, the so-called midnight sun. So you'll never set up at the North Pole. But if we turn off the atmosphere again, we can see Polaris at the local zenith. And obviously the horizon that's shown in this night sky simulator is not meant to reflect the different locations. It just always shows this sort of pastoral scene, right? Instead of course, an Arctic, wasteland. Okay. And while we're speaking about Polaris, someone pointed out that it's not called the Dog Star. I guess I misremembered that. I'll have to find out what it's actually named after. What is the mythology behind Polaris? So I misspoke, and I wanted to clarify. But I don't, that was just meant to be kind of a little extra information, not something we're responsible for. I don't teach the mythology aspects of the stars. So that's why I'm not that well versed in it. Sorry. All right, moving on, going back to the slides. Let's switch back over to there. So there you've seen and if you kind of lost track of why we were looking at Polaris so many times, the idea was that we were seeing how there's a direct relationship between Polaris's altitude in the local sky, so that's how far it is above the horizon, how close it is to the zenith, right? So that value, that coordinate in the local sky, is directly related to your latitude. So if Polaris is at the zenith, then you are at the North Pole. So in other words, just another way to think about those same formulas to relate latitude to declination, in this case with the focus on one well-known star with a well-known declination. All right, so local celestial coordinates. I've already started on this, and in fact, I just used the word altitude for the first time. So we've got so far what we have, right? We've got the hopefully familiar latitude and longitude coordinates on Earth, more as a reference than something that, that I'm trying to teach you. Now we've got declination and right ascension as the actual coordinates on the celestial sphere. Okay, well, there's also coordinates on the local sky hemisphere because you want to be able to locate stars on the local sky in order to do things like relate them to declination and latitude, right? Or rather, relate them to declination and find latitude. Do you see that? You could actually, and that I mentioned it, but that would be the steps. Step one, measure the altitude of a star. Step two, look up the declination of that star because that's a value that you would find, in a reference because stars' declinations don't change. All right, not over a human lifetime. Then calculate your latitude with those two values. Okay. So, what is the altitude? Just to be explicitly clear about it, it is the height as an angle. Everything we've talked about are angles above the horizon. 0 degrees is a star that's located right at the horizon, and 90 degrees is a zenith. All right. So, in Copenhagen, Denmark, the star Vega is located at an altitude of 45.7 degrees and a declination of 38.8. Rome, Italy is about 250 miles south of Copenhagen. In Rome, is the altitude or declination of Vega different than it is in Copenhagen? So, would the altitude be the same of the star Vega? No, no. Yep, the altitude would change. Good. Seems like everybody that ventured an answer, you're right. It would be different. But what about the declination? Yeah, because that is a fixed value. I know I just said it, but I'm glad you're paying attention. Stays the same. Excellent. Good. Nice work. Okay. So altitude is the same, declination is not. I don't I was trying to think about what the hands meant, like if they were trying to give away the answer, but I guess it just meant like I don't know. But you can see, right? They blurred out or faded one that isn't the same and kept the other one solid that does, or rather the one that does change, I guess I should say, and the one that stays the same is the declination. So on the celestial sphere, the stars appear to move in circles around which point? Oh, so think about that. We talked about the circumpolar region. All the stars appear to rotate about your zenith or about a celestial pole. Which one? Don't worry about the thumbs. Oh, you know what? You're right, Alexander. It's meant so you can answer them. So clever. In class, I always have people use fingers, like one finger for A, two for B. But yeah, yeah, oh, that's awesome. And it's really, really well suited to Zoom as well. Yep, it is the celestial pole. Nice. Yep, because the zenith is more arbitrary, right? Yeah, all the stars rotate around the celestial pole, and they don't actually move, right? That's just the apparent motion because of Earth's rotation. The fact that our planet spins about its axis every 24 hours. All right. However, we'll talk about it. Its actual rotation speed is 23 hours and 53 minutes. The solar day is 24 hours. And understanding the difference is going to be another one of those visualization exercises, but we'll get to that in chapter 3. It's not covered in chapter 2. All right. Celestial pole. Nice. And there's a kind of a picture that I had mentioned before, and maybe you knew what I was talking about. You'd seen them in the textbook or elsewhere. And so this is like if you do a time lapse of stars in the sky, this is what they look like. All right. But this is obviously a very dark sky where they're able to see a lot of stars and then time lapsing them as they move. All right. There, it's interesting that they all kind of came out blue here. I'd imagine that's sort of an artifact of how they were captured. Some stars are blue in appearance, but they're not going to appear blue. Not this many would. There'd be more red ones and so on. And it's probably has to do with the again like the way it was captured and kind of like what color is dominating over time. Yep. And there, right, Polaris. And Polaris is not exactly at the celestial North Pole. And this arrow kind of actually does do a decent job of implying that because it's not pointing to the very center. And it is pointing to a streak, right? So it's not exact, but it's within 1 degree. So it's certainly was accurate enough for ancient measurements, and just for approximations is still good today. All right, movement on the sphere. So the apparent movement of objects due to different viewing positions is something called parallax. You probably haven't heard the term before. If you have, that's great. That help with the introduction. But we're going to see it a few times when we talk about astronomical objects, and it's just it's a fairly simple idea, and but it's crucial for understanding why things appear to be at different locations relative to each other. All right, and we'll look at a kind of a picture here. All right. So if you imagine looking out onto a forest with sparsely populated with trees, well, if you stand at one point and you look at these fairly distant trees, they look as they're shown here. But if you move to the side, then you could have sorry for advancing a slide. We'll stay on this one. But if I move to the side, then I could have, say, this tree right here get located behind the tree in the front. So if I continued to walk to my right, I could get it so that the pine looking tree is obscured by the more sort of like a deciduous looking tree that's closer to us, right? Because you could just, you could keep moving until they line up. And actually, I wouldn't move to my right. I'd have to move to my left to do that. So imagine it, right? You got to move to your left until you get them to line up. And you know, you have one now positioned behind the other. So that apparent location of those two distant objects that are themselves different distances from you is the concept of parallax. All right, so here we have looking at a dog. You have a direct line of sight to the dog. Then you have a known distance to a different observing point. So you look directly at the dog, then you move to the left, a known distance, and then you can measure that angle and then calculate the distance. All right. Now, it might show a little bit of trigonometry here, but you won't be responsible for that in the homework. It's just, but if it helps you understand it, that's great. So you've got the hypotenuse, which would be the line of sight after you've moved. Remember that you have the bottom of the triangle is that known distance relative to the angle that's shown is the distance to the dog. That's what you're interested in the case of parallax, because you're going to be using that known distance, which is called the baseline sometimes. So the known distance is called the baseline. That's actually what the term they use for like land surveys and using this technique to make measurements. And so then the opposite side of the right triangle relative to the angle is the desired value, the thing that you're trying to find with parallax. We've got the adjacent side, the known side, and the angle relationship between them is sine. Again, won't be asked to calculate this in the homework, but sine of the angle is the opposite over the hypotenuse. And the angle would be known because you could use any number of tools like, some sort of protractor to actually measure that angle by just, lining things up, by looking at it, making markings. All right. Cosine is going to be the adjacent over the hypotenuse. And then to directly relate the opposite and adjacent is the tangent, which is not, they mixed up two of the animations, but this one's actually showing the tangent, and then this one's showing cosine. All right. And we won't do the exercise because it wouldn't make any sense because you won't have to do it in the homework. But the whole purpose of that is that knowing the distance allows you to make measurements. All right. You're going to have to hold on that idea for a while because we'll come back to it. We have a whole chapter on making celestial measurements, measuring distances, and parallax is really kind of the crucial first step that astronomers use for measuring distances. Suffice to say that the baseline in astronomy is Earth's orbital diameter around the sun. So imagine you make a measurement of a star at 2 months or two points in the calendar that are 6 months apart. And then you use that known distance as your baseline, which is 2 astronomical units. And then you look at the change location of the star. Okay, because closer stars will appear to move in the celestial sphere relative to more distant stars. Does that contradict what I said about declination and right ascension being fixed values? Yes, slightly, but the answers are always less than 1 arcsecond, which is a 1/3600th of a degree. So these are tiny, tiny changes, ones that cannot be observed with naked eye measurements and really need very precise, high caliber telescopes to even discern the changes. But those changes do exist and allow for calculations of distance. All right. So let's bring it back to something that's closer and talk a little bit about how planets appear to move through the celestial sphere. Because the type of movement that we're interested in right now is going to be largely focused on the sun's movement through the celestial sphere and planets. The concept of parallax will help us when we talk about what's happening with how planets can appear to drift backwards through the sphere. So we'll see that in a moment. So an imaginary sphere that surrounds Earth, we already know it's the celestial sphere. Stars live on it. planets, the sun and the moon, move along the surface of the sphere. So they are wanderers. The word planet is a wandering star, is the origin of the word. So over different times of the year, the planets and the sun, planets being shown as the purple dot, the white dot, and the red one, and the sun, of course, the large yellow dot, are moving across the celestial sphere. Okay, not over an individual night, but over many weeks. Their current value of declination and right ascension are constantly changing day after day, right? They change very little over a given day, but if you compare them, between periods that are 10 days apart, there'll be a noticeable change. And that's because Earth is orbiting the sun, right? So our line of sight to these different, certain to the sun itself and how the sun appears to be located relative to the stars. And then, of course, the line of sight to the planets is all changing as Earth is moving. The planets, they're complicated because, of course, they're orbiting as well. So their position is being affected by our orbit as well as their orbit. But since all planets don't orbit at the same rate, we are always catching up and passing one another, right, in our respective orbits. All the planets are. And the overall trend of planetary orbits, we'll talk about that later. I won't get into it now, but it's an idea that we'll return to. So, starting with the sun, great place to start. Natural idea for the importance of apparent motion across the celestial sphere. In fact, it's almost the motion of the sun across the celestial sphere is almost as important as the celestial equator itself. So it's going to create a circle that is a key reference, a key idea of the celestial sphere. So the sun moves across the surface of the celestial sphere, making a complete path once per year. Okay? Because we return to our same orbital position after a year, so the sun returns to its same apparent location on the celestial sphere after 1 year. Okay? So if we were to track it at different points and find its coordinate, in other words, its declination and right ascension value, we'd be able to map it out over a period of weeks. Obviously, this diagonal, rather rectangular picture here isn't showing the celestial sphere, just a portion of it, and it's showing the path, its path. What's important about this is that the path of the sun is moving while the stars remain fixed. That's the key idea. The stars are not changing over the year, right? Not substantially, but the sun is. And that creates, here's the key term for you, ecliptic. It creates the circular path called the ecliptic. This is the apparent path of the sun through the celestial sphere over 1 year. It's 360 degrees. It's a full circle, right? It's got, it's the same, the same like parameters as the equator, but it's tilted. So it's like, if the Earth wasn't tilted, that's a key idea. Maybe you're thinking of it. If the Earth itself wasn't tilted, in other words, if its rotational poles were not tilted relative to its orbit, then the ecliptic would exactly overlay the celestial equator, because of course the celestial equator itself overlays the Earth's equator. But because of the axial tilt of the planet, the ecliptic does not line up with the celestial equator. The maximum angle between the ecliptic and the equator is 23.5 degrees. That angle is the tilt of our planet. The axial tilt of Earth is 23.5 degrees. Therefore, the ecliptic maxes out at 23.5 degrees. Why does it reach a maximum? Because of how the tilt of the planet works. Because the tilt doesn't remain fixed relative to the sun, but remains fixed relative to distant stars. And that's something that you have to see in a picture if that seems like you can't like parse that sentence into an image in your mind, but we will. Okay. So just to reiterate, the sun doesn't move at an angle. Instead, the earth is tilted, making the ecliptic appear angled, right? The sun doesn't move relative to earth, right? The earth moves relative to the sun. So this is all about apparent motion that we're seeing, right? The ecliptic is about the apparent motion of the sun. So looking at Earth, here is Earth's tilt. Notice that Earth's poles, the north and south, are shown here tilted to show that the planet itself is tilted relative to a, a line that passes directly through the ecliptic. So in other words, this label line here, the one that says line perpendicular to the ecliptic, you could think of that as the solar system's pole or the sun's pole. So the sun has a north pole, of course, right? And because actually the sun rotates very quickly. And that north pole of the sun is essentially the north pole of the whole solar system. And the whole solar system is like a disk. All the planets approximately rotate in a plane, in a disk. And they have slight angles relative to that, which come up in certain calculations. And we'll touch on a little bit when we talk about the solar system. And so if you think of that whole disk as the solar system, if you were to pierce a line directly through it, that line is our reference for the axial tilt of Earth. So when we say that Earth is tilted 23.5 degrees, it's tilted relative to the solar system as a whole. At least that's one way to think about it. All right. We'll also come back to, as I said before, thinking about what that tilt looks like at different points in Earth's orbit around the sun, which is why the ecliptic passes through the celestial equator. Okay. So Earth's axial tilt, 23.5 degrees. You got that? Good number to remember, right? Other planets aren't tilted very much. Mercury, almost no axial tilt. Venus, also very small axial tilt. All right. Pluto has a very large one. Uranus has the biggest in the solar system. And by the way, we'll see this again when we have a whole chapter where we look at the solar system as a whole. This is just highlighting the importance of axial tilts. This one's kind of cool though. I always say that it's like Uranus is knocked on its side, so it looks almost 90 degrees. So that means one of its poles sometimes faces the sun. All right. So we saw. I went backwards. I think. There we go. Pluto. Now they're lining them up. So once we got to Uranus, it said, okay, so what do they look like when we take the solar view? So notice this is the planetary view for all of these. So planetary view of Mercury, Venus, Pluto, and Uranus, where we're seeing from the point of view of the planet. All right. But if we turn it for the solar view, well, there's almost complete agreement between Mercury and, between both types of views. Same with Venus, very, very small difference. But with Earth, we saw this before, right? So this is taking Earth and making it so we're seeing it as we would see it from, like the vantage point of being outside the solar system. So if you were sitting in the alien spaceship looking down on the solar system as a whole, Earth would appear tilted, but you'd line up your sight with the plane of the solar system, and so that's what this view represents. Same thing for Pluto, right? And the poles are represented with these blue lines. So you'd notice Pluto is significantly tilted, and as it spins, you would see that tilt, and then Uranus is practically on its side. All right. So let me show you. So yeah, we're doing time. We got about 12 minutes left. I think I'll just shoot for 10. And let me do something real fast. I know these can be tricky ideas to visualize, obviously. So I want to, before we talk about the lunar stuff, show you the axial tilt. We're going to go back. to the simulator. Okay. And I want this one here. And then, yeah, perfect. All right. So then we want, this is showing this I know I'm not sharing the screen yet, but this simulator is going to show us it's called the Basic Coordinates and Seasons Simulator. And the reason for that is because the axial tilt of Earth is the dominant reason we have seasons. That's why we have, winter and summer, because of the length of the day and the intensity of sunlight and how it's affected by the axial tilt of our planet. If we didn't have an axial tilt, there would be almost no change between, substantial change between the weather throughout the year. The whole planet would behave like the equator. All right. Okay. So all that's fine, what I just was talking about with the seasons, but I don't want that to distract the main thing I want to get across here. Remember how I mentioned that the axial tilt is relative to distant stars instead of the sun? That's a common way to define it, but I know it might not be that clear. What it means is that the tilt remains fixed as Earth orbits the sun. So let me show you that. Okay. So here is Earth. Okay. And we can, what's nice about the simulators, we can take kind of different views to show what I want to. Notice the tilt of the planet. Okay. And this is at a particular day of the year, which is labeled accurately. This is in early February. And in early February, what are we looking at here? All right. Well, we're looking at a planet where the northern hemisphere is tilted away from the sun. Okay. You can see that a bit just when you look at the shadow. If you kind of look head on, notice the northern hemisphere and the North Pole is tilted away. So the North Pole would be in perpetual darkness. The South Pole is tilted towards the sun and it's in perpetual light. All right. So that's why we say that February is winter in the northern hemisphere and summer in the southern hemisphere. If we look at this side view, we can see it very clearly because the sunlight is coming in. The sunlight always comes in parallel. All right. And it's going to come in and it's going to hit the surface of the planet and it's going to hit more directly at particular latitudes. And it's not going to hit at all at the North Pole, as I mentioned before, right? And it's going to hit directly, like the sunlight will be coming from the zenith direction at a latitude that corresponds to a little bit south of the equator as I just moved the stick figure. Okay, so those are ideas again that we could elaborate on. But now back to the promised motion. Okay, so notice that tilt. As I go, I'm just going to drag the timeline here to go throughout the year. As I move the year, the planet is going to orbit the sun. Now I want to get a good view where I can try to show this as clearly as possible. Okay, there. I think that worked. So the tilt remains fixed. Okay, so that angle of the tilt doesn't change. It's not like the Earth is tilted towards the sun and then rotates with the tilt always being towards the sun. Instead, the tilt stays independent of the orbit. And I should say revolve, not orbit. It's best to say rotate for the solid object. So the Earth rotates around its axis and it revolves around the sun. But a synonym of revolve is orbit. Maybe if I show it from the top. Yeah, so mostly from the top. Now see if this makes it more clear. So we'll again start in January. So notice the pole of the planet tilted away from the sun, and then I'm going to turn, and it stays. So now, right? It's not like it stays tilted away. As I move down here, now it's tilted towards. So what's happening is the tilt just remains the same, no matter where it is in the orbit. But that means that different parts of the planet are either tilted towards or away. That's the key idea. And that's true of any tilted orbital body. Any planet that's tilted, that tilt is independent of the orbit. So at some point, as you move throughout the year, you reach a point where the tilt is exactly lined up with, like right there. So now notice that the tilt of the planet is lined up with the actual direction of motion, or what's called the tangent of the circular orbit. Another way to say that is that the tilt is perpendicular to the radius of the orbit. And so at that point, we have the whole planet, and we'll make it more exact, is right here. The whole planet is half bathed in sunlight. And that point, which happens twice a year, is the equinox. So that's a way to put this, and maybe this will help explain what the axial tilt is 2 times a year, the axial tilt doesn't matter. 2 times a year, the axial tilt is canceled out because of the orientation of the planet relative to the sun. And those 2 times of the year, the tilt is perpendicular to the radius of orbit. And those 2 times of the year are the spring and fall equinoxes. And it's almost as if on those 2 days of the year, we don't have an axial tilt. And the whole planet from pole to pole experiences 12 hours of sunlight. Okay? Any questions on that? I could easily see some, but any pressing questions that you feel like you could ask right now? Okay. Yeah. So yeah, obviously review it, check it out, yeah. I read the material in the chapter. I think that's a great place to start. Look for videos, starting, including the ones for chapter 2. As we wrap up, I want to point out that we got through just about, actually, let's just finish off with one quick thing with the moon. Yeah, we can squeeze it in. So I'm gonna jump back to the slides real fast. So stick with me for another 4 minutes or so. So let's go back to the slides, because we're at a great stopping point if we just get it there. So then hide the menu here. Yeah. So I had left to talk about what the axial tilt looks like from different perspectives. Where I left the slides, where we left off was, it was mentioning the moon on the celestial sphere. And just to touch on that, the moon also follows close to the ecliptic across the celestial sphere. So it's going to, you know, basically kind of follow that same path. And that's because there isn't a major tilt between the moon and the ecliptic. They're more or less lined up. Um, they're not exactly lined up, which is why we don't have eclipses once a month. But the fact that we have any eclipses where the sun and the moon literally overlap each other, either a lunar eclipse where the moon passes behind Earth, so exactly opposite of the sun, or where the sun passes between us and the moon, or rather, yeah, backwards, where the moon passes between us and the sun and obscures the sun, a solar eclipse. Well, the fact that those are possible is because of that near alignment. So, about how long does it take the moon to make one complete trip around the celestial sphere? So, think about these relative motions. How long would it take for the moon to follow every point on the celestial sphere? What do you think? I guess I should open up the chat unless someone wants to turn on their mic.
I said number 3.
Yep. Yeah. Yep. 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 Nice. Thank you, by the way, for sharing. And Most people agree with you. It definitely it seems reasonable that it could be a year. We're mostly talking about things that take a year. The sun takes a year, but it is indeed 1 month. And that's because we don't need to complete a full orbit around the sun for the moon to complete its full orbit. So that's the thing, is because the moon is moving right around us, its apparent location relative to distant stars. You can just think of like what stars is the moon blocking at any point, right? As it moves through, well-known constellations. Well, that's going to be, take or that full process will take a month until it gets back to where it started. Okay, so that will be a month. And later, once we get into chapter 3 material, we're going to learn a lot about different types of months. Just like I hinted at, there's a different type of day. There's a solar day and something called the sidereal day. There's also a solar month and a sidereal month. So kind of cool stuff. And that'll really build on these same ideas. It's all about all this relative motion, thinking about the importance of angles and rotation, and being able to see it in your head, and hopefully using tools like simulators and good videos to get to that point where it makes sense. All right. And during a solar eclipse, the moon and the sun have the same. I'll give away the answer here, but think about it before I give it away. We have, okay. So take a moment, and both, because they have to exactly overlap. You can't you can't just share the same declination, because then one might be above or below, right? In terms of the altitude in your local sky. So in order for them to exactly overlap, they have to have the same two coordinates, declination and right ascension. I know one thing I'd hinted at that I never circled back around was how right ascension is measured, can be measured in hours instead of degrees, and how that and what exactly the equivalent of the prime meridian is for right ascension. We almost got there because it actually has to do with the equinox, but it's fine, and we can always bring that back in a later chapter, and I won't bring it up in a quiz. As far as kind of accountability, what do I expect you to know? Well, we got it through everything up to solar system models.